Hello, friends. This is Jim with Science Talk. I have an article to discuss with you, and definitely a case of here we go again. So, let me read to you the headline. And now remember, I'm just the messenger here. Okay? New plane can show geoengineering works. Excuse me for a moment. Nope, I'm not dreaming. That's the actual headline. Oh boy, here we go again. With new aircraft, humans could potentially mimic volcanic action, dim the sunlight, and slow global warming, showing that geoengineering works. It's a controversial idea. Ya think? All right. So what's going on here? And I just beat my head on the table just to make sure I'm not in a dream, but unfortunately it's not a dream. So, engineers have designed an aircraft that could lift a cargo of sulfur dioxide to an altitude of 20 kilometers and spray it into the stratosphere to darken the skies, dim the sunlight, and bring down climate change, in an attempt to offset what emissions of fossil fuels, adding carbon dioxide, other greenhouse gases into the atmosphere does. The aircraft has been given the name SAIL, which is an acronym for Stratospheric Aerosol Injection Lofter. And this aircraft could cost no more than $2.35 billion, would it be, dollars a year for airframe and engine, and the first 8 could be available 15 years from now to begin flying 4,000 missions a year. So let's see. We have 8 aircraft. Each aircraft they're planning on doing 4,000 missions a year. So you do the math there. Each aircraft does what, 500 missions a year? There are 365 days in a year. So that means they're doing more than 1 mission per day. Then it's saying by the end of another 15 years, a fleet of 100 such aircraft could be making 60,000 high-altitude deliveries a year. So that means each aircraft will be doing 600 flights per year, or just about 2 per day. Not quite, but just about. So, the scientists and engineers who are coming up with this notion have published an article in the journal Environmental Research Letters. They address the cost and practicalities of what is certainly pretty much one of the higher controversial aspects of climate geoengineering. Now, they're saying that this is necessary because if humans keep burning fossil fuels the way they're going, and if we assume business as usual, then at the bare minimum, global planetary temperatures could increase by an average of, at minimum, 3 degrees C by 2100, maybe 4 or 5. Now, darkened skies do lower planetary temperatures, as we have seen when there's been particularly explosive volcanic eruptions. Mount Pinatubo, no one's around to measure it, but Krakatoa, when it blew up, literally the island just went like that. That cooled down the planet for a while. We know about Pinatubo, and there's been other recent eruptions that have cooled things down a bit. And what happens is they inject cubic kilometers of ash, smoke, sulfur, usually in the form of sulfur dioxide, into the upper atmospheres. Now, for more than a decade, researchers have argued that since humanity is really not showing any signs of reducing greenhouse gas emissions, that a radical form of geoengineering might be necessary. Others have opposed the case, citing possible unwelcome consequences. Yes, that's very likely. But the first question, could it be done at all? And it appears that the answer to this is yes, but not with the existing hardware, so we have to make the hardware. So, okay, so we have the question, could it be done at all? The next question is, should it be done? And this is where the controversy comes in, and I'll discuss that a little more later on. So now, Gernot Wagner of Harvard University says the following. While we don't make any judgment about the desirability of SAIL, we do show that a hypothetical deployment program starting 15 years from now, while both highly uncertain and ambitious, would be technically feasible, possible from an engineering perspective. He says it would also be remarkably inexpensive, $2 billion to $2.5 billion per year. Inexpensive? Well, okay, you say so. I would disagree with that. Gernot Wagner was a principal researcher on this study, as well as an author. His co-author, Wake Smith, who's currently at Yale College, basically said he became intrigued by research that suggested existing aircraft could be modified to lift huge quantities of sulfur dioxide to great heights and then release it. Turns out this is not so, he said. It would indeed take an entirely new plane design by which SAIL could reasonably operate. No existing aircraft has the combination of altitude and payload capabilities that are required to do this. So the solution that these scientists and engineers arrived at was the plane would have the same weight as a large narrow-body jet passenger aircraft, but to sustain level flight at 20 kilometers a second, it needed roughly double the wing surface of such an airliner and double the thrust, with 4 engines rather than the usual 2. At the same time, its fuselage would have to be stubby and narrow, sized to accommodate a heavy but dense mass of molten sulfur rather than the large volume of space and air required for passengers. Molten sulfur, well, that sounds alarming. They then calculated the rate at which such planes could be built and the numbers needed to make a significant difference to global warming. Global projects on such a scale need international agreement, and the 2 authors rule out the possibility that any individual nation could hope to secretly operate such a high-flying program involving so many flights without detection. However, they do not see it as excessively costly. Again, I disagree with that. Given the potential benefits of having average projected increases to radiative forcing from a particular date onward, these numbers invoke the incredible economics of solar engineering. That's exact words of Dr. Wagner. Dozens of countries could fund such a program, and required technology is not particularly exotic. These are his words. So, obviously, there's going to be political tensions involved with such a scheme. Solar radiation management, or the acronym SRM, which is the catch-all term for any plans to cool the world by dimming the sunlight versus reducing greenhouse gas emissions in the first place, is a political hot potato. Let's just leave it at that. And also, it's an incomplete answer. We really don't know if it's going to do as they say. It would, for instance, do nothing to show the increasing acidification of the world's oceans. And it could seriously affect rainfall patterns in so far unpredictable ways. The world has already warmed by 1 degree C in the last century. And we know about the Paris Accord of 2015, that the nations say, well, we're going to try and contain global warming to 1.5, maybe no more than 2. Well, if we're already at 1, and we're actually now at 1.3, we have 0.2 degrees C wiggle room. No, it's not. We're going to blow right past that. So Joanna Haig, who is a co-director of the Grantham Institute for Climate Change at Imperial College in the UK, states the following. Why set out a plan to implement solar radiation management from a date 15 years hence? This plan is a distraction that may well encourage weaker action on emissions reductions by governments in the hope they will no longer be necessary to even do in the first place. Okay, so here's my take on it. I think you know what I'm going to come down on. This is silly. Okay? Now, in the past, there's been some folks who have claimed that aluminum silicate has been released into the atmosphere. Aluminum silicate has reflective properties, and the scheme was that the particles of aluminum silicate would reflect the sunlight back out into space, thereby cooling the planet. The problem with that is that the stuff will eventually wash out, and then the aluminum silicate gets into the soil and just basically messes up the root system. It kills the plants. The plants are not able to absorb water, nutrients, and what it needs to do, along with the CO2 to perform photosynthesis. So some issues on that. Now, there are those who say there's insufficient evidence for this process happening. There are those who say we have the evidence for that. Whether or not that is happening, the very idea is a silly one. You know, I've discussed with you before putting iron filings into the ocean to stimulate plankton productivity, and that turned out to be pretty much a disaster. I've discussed with you these harebrained schemes of let's build a concrete wall around Antarctica to keep the ice at bay and keep warmer oceanic water from melting the bottom of the ice, and you know how stupid all those ideas are. And I'm going to be blunt, they're stupid. So here's the thing. Now, sulfur dioxide. Okay, sulfur dioxide comes out of volcanoes. Volcanoes are pretty much an isolated event. It happens in a region. It blows up, throws all that crap into the air. And yes, there are global wind patterns that disperse it. And yes, there is a little bit of cooling down for a short period. And then the system, once this little perturbation passes, the system then recovers to where it was and goes from there. Here is the difference between this scheme and an isolated volcanic eruption. They're going to do, I gave you the numbers, you know, something like at least one flight a day at first, and possibly up to 2 flights a day. Where are they going to, where exactly in the atmosphere are they going to release this stuff? Are they going to be flying over land? What continent? They're going to be flying over the oceans? What are the latitudes they're flying at? We already know they're going to be up in the stratosphere. So we have an idea of the altitude. What latitude they're going to be flying, and then releasing the stuff. And it's molten sulfur. So if it's molten, that means it's in a refrigerated state. And exactly what is the quantity that's going to be released? All this is not coming out. These are factors we have to consider. So we don't know what the plan is as far as deployment. We don't know the amount, and we don't know how this is going to, if it's really going to do the job. It may cool things down in the short run, but in the long term, if you look at volcanic eruptions in the past, temperatures cooling down have been short-term cooling down. So that means you would have to do what? You would have to keep flying these missions, keep blowing the sulfur into the atmosphere. Well, does that then change the composition of the atmosphere when you do long-term? There are so many variables and parameters that have not been discussed, or at least, I don't think they, to be quite honest, they just designed an aircraft and they come up with this harebrained scheme, but they haven't really thought through what the parameters of this experiment, and let's say this is an experiment. So, this brings us to the idea of chaos theory. And now I have a little demonstration for you. So, and let me tilt this camera down just a bit. If you can see right about here, I have one of these aroma sticks. So what I'm going to do is I'm going to light this. And I hope you can see this on the screen. You may have to adjust the contrast on your viewing screen. What I want you to do is to look at the smoke that comes off the end of this and how it moves about. I'm going to run this for a few seconds. I'm going to stop it and then rerun it. So here goes. No, I'm not a pyromaniac. Okay, now see how the smoke is going? It goes up a little vertically at first. I should shut up because my talking is affecting it. So you can see it, I'll back up. It goes up vertically at first, and then you see how it just kind of crazily distributes itself. Right? So let me kind of kill this here. So many embers flew onto the computer. I don't want that happening. And let's do it again. Again. Now compare how this moved about to the first time I did. I'll even do it a third time. See how it just changes around? Do it one more time. All right. I hope you're able to discern that the motion of the smoke in all three runs, I guess you could say, of this, move the camera back up, was different. So what's going on? Chaos theory. Okay. Why the different patterns of the smoke moving about? Well, there might be micro differences. Well, not might be, there will be. There are micro differences in temperature, micro differences in air pressure. I was breathing. The first run, it kind of went, I inadvertently breathed on it, and look what happened, right? There's an unknown thing being introduced. So that's why for the other two, I basically moved my head off to the side, didn't try to breathe on it. I didn't want to affect it. So we got changes in density, micro density gradients, micro temperature gradient, micro air pressure gradient. This affects how the smoke particles move about. And remember, one of the things they're talking about is releasing smoke, in addition to the sulfur. Okay. So you have the smoke moving about, how it interacts chemically and physically with the surrounding molecules will affect its distribution, along with the micro gradients, etc., etc. Now, Now I did this right here, right? So we have this kind of a region. So that is probably about what, 10 cubic feet of air volume I was dealing with. Now extrapolate that to the atmosphere. How many cubic kilometers of atmosphere there are there? So you're going to introduce the stuff we're not going to really know how it interacts with the other chemical species in the atmosphere, or how the wind patterns, temperature gradients, pressure gradients, density gradients, how that's going to affect the distribution, and whether it's going to have the desired effect. Does it stay aloft? Does it wash out? Okay. Now, often there's a criticism leveled at climatologists saying, well, you guys really don't know what you're doing to your models. Your models are crap. You can't account for everything. To a point, we can't account for everything, but as I discussed in other videos, a lot of researchers will model a situation based on known data, and they keep tweaking the models until the model reveals the results of that scenario. Then when they say, okay, we've got it dialed in, now we can start tweaking a parameter, a variable here or there, and run the simulations. So, but we are getting we know what the variables are, we know what the parameters are. As our methods of measuring and increases our confidence in what we're doing, our models improve. And our models are pretty damn good. Yes, it may be, does temperatures increase by 2.5 or 3 degrees C? Those are, things to tweak out. But in essence, the models are damn good. We know what the parameters are: temperature, humidity, precipitation, pressure, etc. We know what they are. And we get good measurements on it, so we can model it and get accurate models. Now what happens if you throw in a new parameter? Well, we don't know the interactions. Certainly not on a consistent level. I'll give you as an analogy. You have a nice ecosystem. You've got your producers, you've got your primary, secondary, tertiary consumers, you got your detritivores, scavengers, what have you. And basically it's in balance. You might be oscillating around an ideal situation, but it's in essence in balance. The organisms, the vegetation, the animals have all evolved the system. They all got their niche and their role in the ecosystem. Everything goes along fine. Now you toss in a species that is not endemic to the area. Now what happens? It basically screws everything up. Right? It just totally messes things up, and then the system is put out of balance. How many times you've heard of, let's just introduce a predator here to take care of that issue, and the predator has no natural enemies of its own, and they assume they're out of control. Or probably there's nothing to prey on them, or there's no abiotic or other biotic factors to keep them in check. And the numbers explode. Well, this is what's happening here with geoengineering. We're throwing another thing, another parameter, another variable into the system. And to think this is not going to screw things up, there's going to be something that, try as hard as they can to account for all the possible situations, something's going to pop up that they hadn't thought about. And oftentimes has dire consequences. Not only are we throwing in another variable, but we're now throwing in what? We're throwing in other possible interactions that may negate what the attempt to do. So such schemes, all these geoengineering schemes, it really is a waste of time. And I'm surprised that more and more scientists are thinking along these lines. It really should be develop renewables. And yes, there are issues with renewables. I just discussed that in a prior video segment. But we really, if we're going to solve this so that humanity can persist, we really need to drastically reduce greenhouse gas emissions and greatly step up our efforts on green technology. Having said that, though, there's just too much thermal inertia in the system, really, to be off. For whether it's a geoengineering scheme like this or even green technology, even we will stop greenhouse gases right this moment. There's too much thermal inertia that the system will keep warming up. The other thing that's going on, okay, going back to my analogy with the ecosystem, well, the Earth's climate has been in basically somewhat of a state of equilibrium. Glacial periods, interglacial periods, but it still is, it goes from one to the other. It cycles through. Humans have perturbed the system. And the system is trying to find a new equilibrium point, but because of the continual perturbations, the system cannot settle on its new equilibrium point, thereby really messing things up even more so. I mean, look at the different patterns of the smoke, right? That's all due to differences in initial conditions. And just a slight change in the initial condition can result in wildly different outcomes. And that's the danger here. Yeah, throw the sulfur in the air. What's the initial conditions? Every day, maybe if you fly to the exact same spot, the same latitude, the same altitude, you can have different conditions. Not you can, you will have different conditions. And that's going to affect where that stuff goes and what it does. So really not a good idea. Not at all. So once again, other crazy schemes out there. It still comes down to we just need to reduce greenhouse gas emissions. And an interesting, I'll just throw this out here, sort of like one of these crazy points here. When the Isthmus of Panama arose, thereby shutting off the equatorial flow between the Atlantic and the Pacific waters, that helped create the Gulf Stream. And the Gulf Stream bringing warm tropical water to polar regions actually helped initiate the onset of ice ages, because now that water starts evaporating in the polar regions, coming down to snow. Ice is the accumulation, compaction of snow, ice sheets grow, and so on, along with changes in the Earth's orbit. I've finally gotten some good material to discuss with you Milankovitch cycle. I found some good graphics. So that's coming soon. Look for those. But anyway, back to the geoengineering. No, not a good idea. Really should not be pursuing such things. Because we really don't know what we're doing. We really don't know all the consequences. We can think of as many as possible. There's always something else. It's like if I have a two-body system, I can find a nice Lagrange point between them. Three-body system, I can still find a Lagrange point between them. A little more difficult. Get to a four-body system, and it becomes damn near impossible, extremely difficult to do so. This is what we're doing. We're throwing in another parameter, and it's going to mess things up, because it's going to create situations we could not have foreseen, and may actually create another problem. So I wanted to share this with you, that this is some crazy things that some scientists and engineers are scheming up, and it's really not a good idea. I hope that you can see that smoke thing, and I hope that demonstration was useful to illustrate the idea of chaos theory, and that little perturbations in the initial condition can give you wildly different results. That was the idea of that, and now extrapolate that to what this plant is do in the atmosphere, and I think you can see how that's is not a good thing to do. Anyway, kind of a long video. Sorry about that, but wanted to bring this to your attention. Hope you found this video useful, informative, and we'll talk soon. Thank you for your time. Hey folks, this is Jim here, reminding you to subscribe to this channel, to share my videos, tell others of the work that I do here. I also ask that if you are not already a patron at Patreon, to please consider becoming a patron at Patreon. You can find the information in the description box below the video. I'm asking you to help support the work that I do. I do not take any money from corporations or from any other sources, so the information I share with you is the actual science as it comes out of the peer-reviewed journals. So there is no BS, there's no propaganda, there's no agenda. It's just I present the science and I explain to you what it means, or at least my interpretations of it, based on my own experience as a scientist. I want this channel to grow. I consider, while I discuss many different topics here, you notice I do focus a lot on climate issues. I consider climate change to be the most pressing issue facing humanity today. Thus, I consider it important to disseminate this information to a wider and wider, more and more people. And I need your help to do this. So, yes, please subscribe. Please tell others of the work that I do here. Please share my videos on social media platforms, with your social media groups, what have you. We need to get this information out there. So for those of you who are supporting me on Patreon, I thank you greatly for your support and continued support. It does mean a lot to me. So together we can get this information to more and more people. Thank you. Thank you for your support.